Younjin Kim from POSTECH, who used to be at Imohon's University for last 4+ years. Probably. She moved to POSTECH recently, and she will talk about the extremal problems related to Szemerédi's theorem. Please.
So thank you. Thank you for giving me this opportunity to give a talk today. So today I'm going to talk about one of the extremal problems related to the Szemerédi theorem. First, let's look at the arithmetic progression. So let's look at the definition of arithmetic progression. Arithmetic progression is a sequence of numbers that advances in steps of the same size. So arithmetic progression has the following form. This is the arithmetic progression with a step size d. So let's look at this example. 1917 is the certain arithmetic progression with a step size 8. So we choose the randomly 10 integers between 1 and 30. So we choose 1/3 integers among them. So 10 is the 1/3 integers among them. Then is there certain arithmetic progression here? If we choose 10 integers in this way, you can find the certain arithmetic progression 1970. The answer for this question is yes. But if we choose 10 integers in such way, you cannot find any certain arithmetic progression. The answer for this question is no. So how can you find this certain arithmetic progression all the time? 30 is not enough number for getting the certain arithmetic progression all the time. So if we increase the 30 to the big number, such as the 60 million, then you choose the 1/3 integers among 60 million. That means you choose the 20 million numbers. Then you can find the certain arithmetic progression all the time. Actually, it's proved by Szemerédi. So let's look at the Szemerédi theorem. In 1975, Szemerédi proved that every positive integer k, every subset of n numbers with enough size must contain the arithmetic progression with length k. Because of this result, Szemerédi received the Nobel Prize in 2012 when his area was extremal combinatorics. Actually, how can I apply this Szemerédi theorem to the previous question? So in the previous question, you want to find a certain arithmetic progression. So here, k is 3. In addition, we choose the 1/3 integers among them. So delta is 1/3. So actually, using this Szemerédi theorem, we answer the previous question. So let's look at the definition of KAP3. So let's consider subset of n numbers. If this subset does not contain the arithmetic progression of length k, this subset is called KAP3. So we define the size of the largest subset of the set A, which does not contain the arithmetic progression of length k by the RK of A. Then we have, the Szemerédi theorem has the following second formulation. Why? If you look at the previous Szemerédi theorem means that every subset with a size larger than delta n, then it contains the arithmetic progression of length k. So we define that is consists of the n numbers. Then RK of n is the size of the largest subset in n numbers, which does not contain the arithmetic progression of the length k. So here, that is exactly maximum size of the KAP3 subset in n numbers. So from the Szemerédi theorems, if the size of set is larger than delta n, then it must contain the arithmetic progression of length k. So that is the maximum size of the KAP free subset. So it means the RK of these n numbers must it goes to 0 when n goes to infinity. So that is exactly Szemerédi's the second formulation. Does it make sense? In addition, there is another formulation. It's, as you know, just the you consider. I did. Positive density. Then if you have the positive density, then it has the it contains the arithmetic progression of length k. So that is also Szemerédi another formulation. Does it make sense to you? So in 2008, Green and Tao got the Szemerédi theorem for the prime number. So they proved that every subset of primes with enough size must contain the arithmetic progression of length k. So it's their result. They consider the intersection of the set of prime numbers and the set of n numbers. Then, so they prove that RK of this set is goes to 0 when n goes to infinity. So actually, they prove the primes contains arbitrarily non-arithmetic progression. It's the Green-Towers theorem. So let's 상관없는 건가요? So let's look at the value of the RK of M. So what is the RK of M? RK of M is the maximum size of the KAP free subset. So first, let's look at the three case. In 1953, Knowles got the upper bound of the R3 of M. Knowles proved that R3 of M is much less than n of log M. Later, Szemerédi and his Brown improved the denominator term to the log n to the c. So here C is taken by the 1 over 20. Later, Vaughan also improved the upper bound of the R3 of M. The Vaughan proved that this R3 of n is much less than the n of log n to the c with the constant c is the 2 over 3 minus small over 1. The latest is the Sanders and Bloom also improved the previous upper bound as follows. They proved that this R3 of n is much less than n over log n to the 1 minus small over n. Let's look at the Sanders and Bloom's just more carefully. So in 2011, Sanders proved that this R3 of n is much less than the n times log n to the 5 over log n. Later, in 2016, Bloom improved the previous Sanders upper bound as follows. So it's needed in the Bloom in CSS to obtain the following current best upper bound. In 2012, the Bloom and CSS to prove that this R3 R3 of n is much less than n of log n to the c plus 1, thus for some constants c. c. That is the current best upper bound. So let's look at the lower bound of the R3 of n. In 1946, the parent got the following lower bound of the R3 of n. And 17 years later, Elkins improved the previous parent lower bound as follows. So actually, Elkins improved the previous lower bound by a factor of the root of log n. So let's look at these two values. Then you just check that the Elkins lower bound is made from multiplying the root log n to the previous parent lower bound. Actually, in 2010, with Green and Wolf provide the show proof of the Elkins result. Let's need the Bloom and success provide the following conjecture about this one. Actually, if you look at the lower bound of the R3 of n, then you just check the lower bound has not been significantly improved. Because if you look at these two results, there is only improvement in the factor of the root log n. So however, in the upper bound, there are a lot of improvement in the upper bound of R3 of n. Because of that, is the Bloom and Sisesk believe that they just think that is the lower bound is much closer to the truth than the upper bound. Let's look at this lower bound. If you look at the Boland lower bound, the Boland lower bound has the following form: exponent minus constant term times log n to the 1/2 times n. Also, after multiplying the root log n to the previous Boland lower bound, we get the Elkins lower bound. The Elkins lower bound has the following this form. Because of that, is exponent. No, the minus constant times log n to the constant times n is exactly lower bound form of the R3 of n. So they believe that their upper bound will be close to their lower bound. So their conjecture. So let's look at the general case Ik of n. So Ik of n is the maximum size of the KAP free subset. So upper bound, I've seen a steady stream of substantive improvement. In 2001, Gauss proved that for every positive integer k, every subset of n numbers of size and list n of log n to the ck must contain the arithmetic progression of length k. So here, k can be taken by the 2 to the minus 2 to the k plus 1, k plus 9. From this result means that this result exactly means that Rk of n has the following upper bound. So from this result, in 2001, Gauss got the following upper bound for the Rk of n. Because Rk of n is the maximum size of KAP free space. Because of that, this result exactly means that the Rk of n has the following upper bound. So Rk of n is much less than n of the log n to the ck. So here, ck can be taken by the 2 to the minus 2 to the k plus 9. So that's this result is the current best upper bound. So sorry for that. And let's look at the lower bound of the Rk of n. In 1961, Jenkins proved that Jenkins obtained the following new bond. It's the Jenkins new bond, and in addition, in 2010, O'Brien improved the previous Jenkins new bond as follows. The improvement of the earlier work is in the simplification of the construction in the node. So if you look at the O'Brien result, you just check that O'Brien to the no bound is no bound improvement is in the simplification of the Jenkins construction in the node. If you look at these two values and you just check that the O'Brien's improvement is the simplification of the previous Jenkins construction in the node. So now let's look at the numbers of the KAP free subset. So let's look at the definition of KAP free subset again. So we consider subset of n numbers, and if this subset does not contain the arithmetic progression length k, this subset is called KAP free, and we define the RK of n as the maximum size of the KAP free subset in the n numbers. Then in 1990, Cameron and Erd H were interested in counting the number of KAP free subsets in n numbers. So they conjectured the number of KAP free subsets is as follows. So now, so we define the number of the KAP free subset in n numbers by RK of n. Then this RK of n is bounded by the sum of the and choose I. The I is from 0 to small ik of n. Here ik of n is the maximum size of the KAP free subset. So via the careful calculation, this sum is bounded by the 2 to the big of the RK of n times the log n to the n of k minus 1. So with the previous Cameron Erd H conjecture exact means that the number of the KAP free subset or large RK of n is as follows. So now, actually, in 2017, the Paulo Luz and Siste, so Paulo Luz Siste answered this question. So they proved that for infinitely many values of n, the number of the KAP free subset of n numbers is the 2 to the big of RK of n. They just believe that they can delete the log n to the 1 of k minus terms in the exponent term. So they just delete this term. So they just got this result. So let's look at the definition of corner. So we consider a set of the three points in the two-dimensional grid. So the set of the 3 points has the following form: the A1, A2, A1 plus D, A2, A1, A2 plus D. Then you just check that every point is made from the first point after adding D to each coordinate. That is the corner. In 1974, Szemerédi proved that every subset of the two-dimensional grid with enough size must contain the corner. Later in 2003, Solomos provide a simple proof for the theorem of Erd H and Szemerédi. 어디로 가요? In 2006, Solomos provide the simple proof for the theorem of Erd H and Szemerédi using the triangle removal lemma. And in 1991, POSTECH and Katz-Nelson to extend the previous theorem of Erd H and Szemerédi to multi-dimension as follows. They proved that every subset of the k-dimensional grid with enough size must contain the k-dimensional column. So let's look at the definition of k-dimensional column. Actually, so let's consider k plus 1 point in the k-dimensional grid. Then a subset of the k plus 1 point that has the following form. This set of the k plus 1 point is called k-dimensional corner. So let's look at this k plus 1 point. So you just check that every point made from first point after adding d to each coordinate. So second point is made from first point after adding d to each coordinate. So let's look at this example. That is the three-dimensional corners. Three-dimensional corner consists of the following 4 points. So this 4 point, if you look at this 4 point, you just check that every point made from the first point after adding d to each coordinate. But in POSTECH, Katz-Nelson did not specify the space bound for n using the algebraic theory. So later,
when you define the corner, do you want d to be positive or d to be non-zero?
these two positive.
So it's different from two-dimensional case?
The two-dimensional case is just the 2 point.
In the previous slide, it was non-zero.
It's non-zero?
Yeah. You went too far.
Where's the definition?
Oh, yeah.
Oh, yeah, positive. Yeah. So, do you understand the definition of the k-dimensional column? But if you look at these pictures, you can figure out the definition of the k-dimensional column more carefully. It's not difficult. Yeah. In 2007, Gauss provide they provide the first proof with the discrete bound for n. In the previous result, POSTECH and the Katz-Nelson result, they did not provide the discrete bound for n. They also used algebraic theory. However, here they did not use the algebraic theory. So that is also their result is provide the first proof not based on the algebraic theory. Also, they actually used the combinatorial proof by establishing the regulated lemma and counting lemma for all uniform hypergraphs. And also, they Gauss proved that this theorem implies the multi-dimensional Szemerédi theorem. So let's look at the multi-dimensional Szemerédi theorem. Actually, in the same papers, Gauss proved that Gauss extended the Szemerédi theorem to multi-dimension as follows. So he proved that every subset of k-dimensional grid with enough size must contain the subset of the following form. Actually, this multi-dimensional Szemerédi theorem was proved by the POSTECH and Katz-Nelson in 1978 using the Erd theory. However, they did not get the discrete bound for when. Actually, in 2007, Gauss is to provide the first proof with the discrete bound for the multidimensional Szemerédi theorem. So they used the combinatorics proof, and they actually established the neglect lemma and count lemma for all-uniform hypergraph. But this bound is very weak compared to KAP3. This bound is very weak compared to Szemerédi theorem, and then it also gives a common time dependence of the initial parameter. So actually, the similar result made by Lego and Noodle the shop in 2006. So let's look at the definition of the corner free. So let's consider subset of two-dimensional grid. If this subset does not contain the corner, this subset is called corner free. So we define the set of elements as the maximum size of the corner free subset in the two-dimensional grid. Then, neatly, the grid get the following current best no bound for set of n. Let's look at the no bound of set of n. So actually, what is the set of n? Set of n is the maximum size of corner free subset in the two-dimensional grid. Then, for the no bound of the set of n, in 1946, Bellman obtained the following no bound with the n scalable 2 to the n1 plus small of n, small of 1 times log n with a constant term. n1 is to 2.828. So neatly, listening the linear and the Chevron to improve the previous Bellman no bound. So actually, they provide the new construction for the no bound of C2 of n. So they improve the constant term, this constant term error to the 2.402. So that actually they improved the previous, the best no bound, and then Nizhny also Gauss extended the previous linear and Schrödinger construction. Actually, the Bangalore also extend the previous no bound as follows. They just extend the constant term to 1.822. This no bound is the current best no bound. Actually, on the green, it just used the construction of linear Schrödinger result. In addition, they just simplified the result without using the entropy method. So the linear Schrödinger method is used. Entropy method is their construction is their result is more complicated. However, Bangladesh result is just one-page result. So the able to Bangladesh result is the current best no bound for the C2 band. Sorry for that. So recently the Bangalore got the current best no bound as follows. So he extend the constant term to 1.822. So in the photo upper bound in 2006, Hypergraph they got the following current of best upper bound. So he proved that the set of n is less than n square over log n to the L2. L2 is still 1.0.01737. So now So now let's look at the numbers of k-dimensional corner-free subset. So let's look at the definition of k-dimensional corner-free sets. So if you consider subset of k-dimensional grid, then if this subset does not contain the k-dimensional corner, then this subset is called k-dimensional corner-free. So Ck of M is defined as the maximum size of k-dimensional corner-free subset in the two-dimensional grid. And in the previous slide, I already mentioned the question of the Szemer and Erd H. So they're interested in counting the number of KAP free subset of n numbers. So they conjectured the numbers of the KAP free subset of n numbers is as follows. So we are interested in solving the natural higher dimensional version of the question of Szemer and Erd H by counting the k-dimensional corner free subset in k-dimensional grid. So let's look at this picture. So if you look at this picture, Szemer and Erd H's question is about counting the number of KAP free subset. So that is exactly the counting version of Szemerédi theorem. So that is actually for this question in 2017, borrowed heuristic and solved this question. In 2007, Gauss extended the Szemerédi theorem to multi-dimension. So Gauss obtained the multi-dimensional Szemerédi theorem. So we are interested to extend the conjecture of the Szemer and Erd H to multi-dimension. That is exactly this missing part. So this missing part is also counting version of multi-dimensional Szemerédi theorem. So I'm going to explain what I did for this missing part. So let's look at this result. So here Ck of M is defined as the maximum size of k-dimensional corner-free subset in the k-dimensional grid. So we get the full infinite and many value of M. The numbers of the k-dimensional corner-free subset in the k-dimensional grid is 2 to the big of Ck of M. That is the higher dimension version of the conjecture of the Szemer and Erd H. In addition, that is exactly counting version of the multi-dimensional Szemerédi theorem. Actually, we used the hypergraph container method. The hypergraph container method is the one technique for rounding the size of the finite objects satisfying the certain properties. Actually, in this method, it's important to find a good connection of containers containing the finite object.
If I recall, the conjecture for Rk of n was that the number of in this context is the conjecture is 2 to the 1 plus little 1 times Rk of n, and the bound that's known as 2 to the big O of Rk of n. Is this?
So you are talking about the bound of the Rk of n?
The counting version, that the number of k arithmetic term, the number of KAP3 subsets there was still a gap. If I remember,
yeah, the 2 to the big of the Rk of n.
Yeah,
For infinite. Yeah.
What's known as 2 to the
Yeah,
big
there is
O
a-
was conjectured as 2 to the 1 plus little 1.
Yeah.
Do you think the same thing should
Actually, they just prove the weaker version of this one. They just prove that it's for infinity many of them, but that means that is just to the big of the archive. That is not exactly conjecture of the Cameron. That is just weaker version of that conjecture. They just answer this
This
question.
is very
Yeah, also there is another other is multi-dimensional version of the multi-dimensional version of the Erd Cameron conjecture. However, that is not exactly the multi-dimensional of the Erd Cameron conjecture. That is just weaker version. Yes, good question. So, yeah.
Was it 1 plus literal 1 or was it?
No.
Big O.
Big O, yeah. It's still recovered. It's, yeah.
A sequence of very sparse sequence of numbers of choices
and
where that holds. So even for all sufficiently large n, that would be quite interesting.
Okay. So when these two, then this theorem exactly is your theorem?
In one dimension, yes.
In two dimensions. Wasn't yours was two dimensions? I see. Okay. I see.
Actually, if you look at these pictures, you can note his nature more carefully. His result is exactly a count version of the Szemer theorem. So that is, my result is exactly a counting version of the multi-dimensional Szemer theorem.
Would you get it for arbitrary patterns, like the multi-dimensional Szemerédi version? You could start with any set X and then take dialects of that. Can you also do that with?
Yeah, so I'm going to explain what I did to prove of my result. So you can see how to prove my result. Actually, I had only 15. Oh, really? Oh, yeah, I see. Because when I prepare for my talk, I just think that I just prepare my talk for 15 minutes. So I think there is. I don't need to concern about time. Just think about that. So let's look at the example, how to use the hypergraph container method. So it's just example. So let's consider set S. So for any two numbers in the set S, the sum of any two numbers is not in the set S. This is called the sum factor. Here, two numbers x and y are not necessarily distinct here. In addition, let's consider this triple. The one number is the sum of the other two numbers. That triple is called the short triple. In 2004, Green got the container number, following container number for some presets. So Green proved that he can find the good connection of containers satisfying the following three properties. First property is every sum preset must contain in the sum container. The second property is the size of the set of container is very few. And third property is each of the containers must be almost sum-free. So let's look at the container number for sum presets more carefully. So first we consider three uniform hypergraphs with the following hyperedges. So if you look at this following hyperedges, this hyperedges consist of the following triple. So here, one is the sum of the other two numbers. That is exactly short triple. So if you consider subset, this subset does not contain any numbers of the connection of the all short ripple. This is exactly some preset, and this subset is called independent set. So here, instead of counting the sum preset, we just try to count the independent number in hypergraph. So so each of container is also almost independent set. So let's look at this one, the container number for sum preset. We just change it from the sum preset to independent sets in the hypergraphs. First, we just construct the hypergraph for our object. Then, we just try to count the independent set in this hypergraph using the hypergraph container method. So here, first, you can find this good connection of containers satisfying these three properties. The first property is that every independent set must contain in some container. In addition, the size of set of containers is few in F. Each of containers almost independent set. So let's look at the hypergraph container method, k-dimensional corners. So I already mentioned the definition of k-dimensional corners. As a first, we consider the k plus 1 uniform hypergraph encoding the set of all the k-dimensional corners in the k-dimensional grid. So here, in this hypergraph, this hyper-edges consist of the k-dimensional corners in the k-dimensional grid. So that means if you consider independent set in this hypergraph, that is exactly the k-dimensional corner free set in the k-dimensional grid. See, in the hypergraph container method, you count the independent set. So here, independent set in this hypergraph is the k-dimensional corner preset. Does it make sense? So let's define the number of hyper-edges in the hypergraph containing the set A by the dig H of A. The maximum degree of the set of T vertices in this hypergraph by the delta T of H. This is the maximum number of the hyper-edges in the hypergraph with a size T. So the co-degree of the hypergraph is defined as follows. H is the R uniform hypergraph of order D and average degree D. Then the co-degree of the hypergraph is defined as follows, using the maximum degree of the set of the J vertices, delta J of H. So let's look at the hypergraph container lemma for k-dimensional corners. So first you consider k plus 1 uniform hypergraph encoding the set of all k-dimensional corners in the k-dimensional grid. Then, if you can find epsilon and tau satisfying these two properties, the first property is the tau is bounded by 1 over 200 times k plus 1 times k plus 1 factorial square. And second property is the co-degree of this hypergraph is bounded by the epsilon over 12k plus 1 factorial. Then, if you satisfy these two, you can find the epsilon and tau satisfying these two properties. Then, you can find a good connection of the containers satisfying these three properties. The first property is the k-dimensional corner free set must be contained in the some container. Second property is the size of set of container is few. And third property is the each of container must be almost k-dimensional corner free. So that means that the number of k-dimensional corners in the set of container is almost epsilon times the number of hyper this hypergraph. That is the hypergraph container lemma for k-dimensional corners. In addition to, although hypergraph container method is important method for proving our result, then there is another second main ingredient for proof of our main result. That is exact supersaturation result for k-dimensional corner. So let's look at the following supersaturation result for k-dimensional corner. So we prove that is any set A in the k-dimensional grid with a side and this constant times the ck of n. Ck of n is the maximum size of the k-dimensional corners. Here, we define the number of the k-dimensional corners in the set A by the gamma k of A. So number of the k-dimensional corners in the set A is the superminimum in M as follows. That is the supersaturation result of the minimum value of numbers of the k-dimensional corners for any set A in the k-dimensional grid of size zeta of the ck of n. So let's look at our main result. So actually we get the number of the k-dimensional corner traces of the k-dimensional grid is 2 to the big of ck of n to infinite many value of m. That is exactly the natural higher dimension version of the question of Szemer and Erd H. That also is the accounting version of the multidimensional Szemerédi theorem. So actually the full proof of our proof, you use the hypergraph container method for k-dimensional corners. Also, we use the supersaturation result for k-dimensional corners in the set of the size of zeta of ck of n. So let's look at our proof. So first, we consider k plus 1 uniform hypergraphs, gk plus 1. So encoding the set of k-dimensional corners in the k-dimensional grids. So here, it means that if you look at if you consider hyperaxis, this hypergraph, this hyperaxis consists of the all k-dimensional corners. So it means in independent set in this hypergraph is must be all k-dimensional corners in this hypergraph. So let's go back to our hypergraph container method for k-dimensional corner. So if you look at this hypergraph container method, if you can find the epsilon and tau satisfying these two properties, then you can find the good connection of the container satisfying these three properties. So we define the epsilon and tau n as follows. Then you can get the following result. So tau of n is bounded by the 1 over 200 times k plus 1 times k plus 1 factorial scale. It's the codegree of this hypergraph is bounded by the epsilon n over 12 k plus 1 factorial. So we get the this result. So we found the epsilon and tau satisfying these two properties. So now we can apply the hypergraph container method here. So now if you apply the hypergraph container method, then you can find the good connection of containers satisfying these three properties. So first property is the k-dimensional corner presets is most contained in some container. Second property, the size of set of containers is very few. Third property, each of containers almost k-dimensional corner free. So that means the number of the k-dimensional corners a set of containers at most epsilon m times n to the k. So from the third property in the hypergraph container method, so each of containers must be almost k-dimensional corner free. So for every container A, the number of k-dimensional corners in the set A, that is the gamma k of A, is at most epsilon times n to the k. So now you can apply the supersaturation result. How? Let's go back to supersaturation result again. If you look at the supersaturation result, that means every set A, any set A in the k-dimensional grid of size at least constant times ck of n, then number of k-dimensional corners in the set A, that is the gamma k of A, is larger than epsilon n times n to the k. That is a supersaturation result for k-dimensional grid. So we got using the supersaturation result, we got the following size of A. The size of A is less than constant times ck of n. Right? If not, is the size you can get the set A with a size larger than constant times the ck of n. Then you can apply the supersaturation result for k-dimensional grid. Then the number of k-dimensional corners in the set A, the larger than epsilon n times n to the k. But here the number of k-dimensional corners in the set A is at most epsilon times n to the k. Because of that, we get the following the result. The size of A is less than constant times the ck of n. So from the first property in the hypergraph container method, every k-dimensional corner free set is contained in some containers. So the number of k-dimensional corner free subsets is at most sum of the to the size of A. That is the bounded. This sum is bounded by the sum of the size of the set of the container and times maximum of the to the size of A. Here, previous result, we get the size of A is less than constant times the ck of n. Because of that, this value is bounded by the to the constant times the ck of n. So we get this number is the to the big of ck of n. So that is proof of my result. Actually, if you are interested in the more detailed proof, so already you can find this result archived. It's 20 pages result. So maybe we will, yeah. Anyway, thank you for listening to my talk.
Thank you. Any questions?
Can I ask some questions? I mean, when I hear, I'm not in this area, but when I hear about this talk, I thought these are the kind of efforts try to understand what this KP free set looks like, or also what this the high dimensional corner free set actually look like. So does your result or other series of results which show the upper bound tells us in some sense like in more intuitive way what these sets actually look like, and then how, just this summation result also tells us if you collect all these in some count examples, what their collection actually look like. That's I think what people try to achieve. So would you give me some intuition about these kind of informal explanations about what I know it's very hard. Yeah, they are talking about in some sense counter examples, large counter examples, collection of counter examples. Yeah. And I want to understand what they actually look like. I don't know, it's a very great question, and then these numbers actually give us some answers about this. But But just see the numbers, I can't really gain this inside you.
So this is the this particular problem. There's no structure probably. No saturation.
You got a question? Lady?
Can you apply your method to make the big O of CKN to be, the coefficient to be smaller and while giving more scores or sequence of n? Can we apply your method to make the coefficient and the big O of CKN smaller or whether just obtaining sparse or sequence of n?
Oh, not that. This is not that.
So, what is your question exactly? So we are talking about forgetting that this result is
I think the question is, can we sacrifice coefficients and have more integer n? You have this infinite sequence of
yes.
but can you make it like more?
I mean, why making that sequence more sparse? So can you achieve smaller constant and the exponent?
Oh, the other direction. I see. So
Yeah.
so you want to reduce the C prime while making the sequence like more sparse.
Actually, for that is you need to think about another supersaturation result and should be more difficult. Well, we could try it.
There was another question, right? Was there a question there? I have a question. So, so in your hypergraph container lemma, what is so special about k-dimensional corner? If I change it to any other property, then is the proof become harder? Or?
Actually, that is used by the hypergraph container method. Container theorem is still Sexton, Thomas, result 2015, the invention. So they just mentioned, they just get the hypergraph container name exact for any hypergraph. That is their result. I just used their result. However, forget the hypergraph container number for k-dimensional corners, we can find the epsilon and tau satisfying this property. So they just this hypergraph contains theorem is to for any hypergraphs satisfy these two properties, and you can find the good connection of containers satisfy these three properties. So as you know, the hypergraph container method is the first property is any independent set in the hypergraph. Also, the must contain any some containers. Here, in the hypergraph container method is independence. They just count the independent set in the hypergraph. Actually, it's very difficult question to construct some new hypergraph container.
Completely new, different constant, or consequence of the theorem?
That is very difficult question for construct a new hypergraph container lemma method for.
Let's take a speaker.